Hi everyone, I'm going to share the procedure and the outcome of predicting with machine learning the power output of a combined cycle power plant from a site dataset. After studying the dataset and understanding the assessment, we learn that this is a regression task with supervised learning. We have labeled data that will be put into the machine learning to learn its features and derive the relationship in order to make a prediction of our target electrical power, a continuous numeric output. Before selecting the algorithm, we pause for six key considerations. This regression task requires regressions, algorithms, and metrics. We saw about 1% outlier, so we must monitor both RMSE and MAE while keeping an eye on the residual near the extremes. In a business context, shortfalls are heavily penalized, so we choose a more conservative forecast, minimizing the variance and allow a more conservative bias to avoid shortfall during uncertainty. Stakeholders need to trust and audit the forecast. We must prioritize interpretable baseline and accuracy for accountability. We report the RMSE in megawatts as a primary business metric so operation can gauge the real impact. We will use the same split pre-processing pipeline and output metrics for each order so that the comparison is fair. We have selected three sets of algorithm. Lasso regression for a strong interpretable baseline with built-in feature selection, K-nearest neighbor regression to capture the local structure after scaling, as well as the similarity-based prediction for in the case that this is a non-linear relationship. Decision tree regression for white box interpretability, and as well as a non-linear splitting without scaling required. We understand that the combined cycle plant is actually two tightly coupled machines. Density in, pressure out. Dense intact air boosts the gas turbine, and low condenser pressure boosts the steam turbine. Anything that reduces intake density or rises condenser pressure will pull the PE down. In our pair plot, we observe moderate positive relationship between AT and V. There's also a very clear positive linear trend between the AT, V, and the target PE. AP and RH show very weak relationship, but noticeable. So they are essentially independent. We can keep both features. In a heat map, there's no single pair redundant enough to drop a feature outright. Because of the ATV collinearity and the weather-coupled effects, we favor models that are more robust to correlations and can learn local patterns. That is what we saw in the results. After the three model testing, the final pick was KNN. It was accurate and well-behaved under the correlations that we have just reviewed. Our model choice respect both the physics and statistics. We kept all four features. AT and V are primary. AP and RH like independent signals. This relationship also motivates the model's choice you'll see later, a model that can capture local structures and tolerate correlated predictors. In model, lasso regularization has kept all four features, signaling that they are sun-independent predictive signals, even if it's correlated. The optimal regularization level chosen by cross-validation wasn't high enough to push bigger features to zero. In multi-collinear setting, with high signal, lasso tends to string coefficients but may not evaluate, especially if all features help reduce error. To evaluate our model performance, we use root mean square error as the primary metric because it expresses prediction error in megawatts, making it easy to interpret in our power plant context. It also penalizes large mistake more due to the square error, and this is good for power energy where peaks matters. We use R square as a secondary metric to measure how much variance is explained by the model. In our dataset, we have almost 9,000 samples. It is not huge, but it's enough to benefit from resampling. And there's also slight correlation between all variables. Cross-validation can average result over multiple folds, which reduces variance and bias in performance estimates.
To start, we ran a quick data health pass before any modeling. All the 5 columns are float 64. Reported values fall within the expected physical range in our schema, and flag out outliers in 2 ways. Z-score are more than 3 in 58 rows. For interquartile range, there's 100 rows.
We evaluated the tree regressor, lasso regularized linear regression, k-nearest neighbors, and decision tree. K-nearest neighbor is our pick. In its result, the predictive deviate from the true PE values by 2.41 units on average, explaining 95.9% of the variance on the test set. The distance weighting with Manhattan distance likely helped capture local structure without overfitting. This balance of low error and high determination of confidence indicates strong generalizations. For our decision tree, it is competitive, but slightly worse than KNN. The deeper tree fits non-linearities but introduces more variance. Regularization via the minimal sample width mitigates overfitting.